Hello, I'm Andrew Lookingbill, and today it's my pleasure to welcome Professor Marcello Canuto to Talks at Google. Professor Canuto is currently the director of the Middle American Research Institute and professor of anthropology at Tulane University. His research has focused on ancient household and community dynamics and the development of socio-political complexity in ancient societies. His primary research interest has been the Maya area, and recently he's used remote sensing technologies like light detection and ranging, or Lidar, to glean new insights about the ancient Maya and their society. Welcome, Professor.
Thank you so much for having me today.
Professor, it'd be easy to focus on the technical details of the work because they are impressive and we will get there. But before we talk about the LiDAR surveys, let's take a step back and focus on the bigger picture. You're lucky in that in your line of work, you're a time traveler of sorts. Can you help us picture what it would have been like standing in the middle of what is now the Maya Biosphere Reserve? Can you tell us about what we would have seen around us?
Oh, that's a great question. And it's something that, in fact, whether archaeologists say it or not, it's something that they're always thinking about, trying to think about what does it look like, right? And it's one of those images we're so used to seeing archaeological sites and kind of their bone color, right? The stone and so forth. But we know that these places were vibrant, colorful, noisy, maybe even smelly places, right? And so an attack of all the senses. And so that's something that we're always trying to do, and it's very hard to do. The area that we work in, or that I work in and my colleagues work in as you said, the Maya Biosphere Reserve, is something that is very different from the kinds of places that we tend to think of when we think of ancient civilizations. I have a few images here of what are reconstructions. You know, these are wonderful little reconstructions of places that most of us, when we were in high school and learned a little bit about ancient society, the ancient civilizations of Mesopotamia or the Indus Valley and so forth. And they are all these wonderful places that tend to be arid, dry places, because European society and European Western civilization came from these early experiments in urbanization and complexity. And so we know about places that are pyramids and ziggurats and other places that are very arid and had their own ways in which humans would have adapted to these environments. The tropical zones, like this one where I work, this is what it looks like today. And thank goodness it looks like that today still, because it means preservation and a wonderful kind of ecology. Obscure that and make that very difficult for people to imagine, right? And the white temple, the white colored temple here that pops out of the forest canopy would not have at all looked like this back when the Maya were at their peak in the classic period. Much of this forest would likely have been cut because people don't live in forests. They live in open areas, and they would have needed this land for cultivation. That pyramid would have been painted, or would have been stuccoed and then painted with all sorts of vibrant colors, reds, greens, and yellows especially. And you would have had people milling around and walking about this region. The region that we're talking about is this area here, that basically covers what is Guatemala, Belize, southern Mexico, and in some ways, some parts also of Honduras and El Salvador regarding largely classic Maya civilization. But the sort of lowland region are basically Belize, Mexico, and Guatemala today. And much of it is still covered by a pristine forest. So these are the kinds of things that we don't see very well. But thanks to certain technologies that we'll talk about, we're beginning to get a sense of it. And an example that has been often used as sort of analogous is in Southeast Asia, in Cambodia, the Angkor, and the various mega cities, right? And you can see on the left here, on the upper left, an image of Angkor, and all of this water and waterworks. These are all artificial, constructed by humans, and now these technologies are allowing us to see this. But when we think about what would these cities have looked like, or what would these places have looked like, how the places teeming with population and so forth, we have a sense that we call them garden cities. It's a term that we use to discuss urbanism in a way that isn't exactly how we might conceive of it in Western civilization. That is, cities that are in a mixture of houses, horticultural gardens, dams, hydrological features, temples, ceremonial areas, open spaces, but also then some agriculture, terracing, and other kinds of works. And so you create this kind of mosaic landscape that would have had people both living, working, if you will, and also then visiting and conducting different kinds of activities. The Maya themselves gave us images to tell us things about them, what they did, and how they interacted. And these are just images from a site in Mexico called Calakmul on the left, and on the right is from a vessel. Look, and you can see that it's basically market type material. This isn't gods, this isn't sacrifice, this isn't warfare, all of these exceptional or extraordinary events. These are people eating, drinking, getting ready for market, trading, exchanging goods, and so forth. So we know that these places had all of these kinds of activities. And just from these murals, you can see the colors, right? It's not green and white. It's all the kinds of blues and reds and so forth that make up life. When you think about it. So a lot of our work goes into trying to recreate images of this kind. This is from National Geographic, and it's a site of El Mirador, where we see workers cutting the limestone bedrock to make material for construction, people hauling it to another spot, sort of a central street like a causeway where people interact and coming in and out of a city, temples in the background that are obviously part of the skyline, but all sorts of other buildings in and around. And of course, these other types of images where you have images of kings and queens, of elite and royals at the top of a temple, looking down at one of these open spaces, and you can sort of see from another angle the kinds of crowds that they could assemble, as well as then the roads leading to them and away from them, and so forth. So yes, these would have been vibrant places with people going in and out, people living nearby or right in there, not just nobles, not just farmers, but a whole mix of other specialists, ritual specialists, crafts specialists, military folks, even people like architects and so forth that would have worked in and interacted with different strata of society on a daily basis, and then on a more sort of kind of a rhythmic basis of going in and out over a period of almost 1,000 years. So these were vibrant places with lots of people living and working in nearby.
Well, thank you. That's exactly the sort of trip in time we're curious about. But now let's talk a little bit about that time machine. As a quick introduction for many of us, can you tell us what Lidar is and what the significance of the aerial collection platform is?
Sure. So we go from these wonderful images to something that is pretty mundane, which is a picture of a tool, right? But Lidar is a tool that has been used most recently in archaeology. It's a technology that's been around for several decades now, and it was only recently applied to the region where I work by some colleagues of mine who work in Belize, Arlen and Diane Chase. And the technology is one that allows, the way it's understood is it penetrates the forest canopy. Now, it doesn't penetrate the forest canopy in that specific sense, but it does shoot pulses of light at such a density that some are able to penetrate the canopy and bounce back. Now, the basic physics of it is light travels at a certain constant speed. If it hits something and bounces back, that time that it takes to go from where you are back to you can give you the distance that you are from that object. So this sensor shoots these lights, these pulses of light, lights that come in and then bounce off the ground or the canopy from a plane, right? From an elevated platform. A plane, usually, sometimes it's a drone, sometimes it's a helicopter, but in our case, a plane, which is the best sort of negotiation of time, energy, and speed, and so forth. And so this plane flies at a kind of a standard elevation and shoots these pulses of light from about 650 meters above sea level down, or above ground level, down to the ground. And if anyone's ever been in a jungle, no matter how thick the canopy is, if you lie on the jungle floor, not something I recommend, but if you do, and you look up in the middle of the day, you will still see little points of light, because light is penetrating through the canopy through, a combination of little holes made by all the leads, right? Those little holes that regular light can come through are the same holes through which lasers, the sensor is sending pulses. And so what essentially happens is that this sensor flying overhead in a plane, in a single engine, fixed wing plane at a standard elevation, is basically showering an area with millions of points at a certain rate. I can't remember exactly the amount. And about 95% of them bounce back because of foliage. So what's known as the crown return, the top of the canopy, bounce back. There's also an understory, which is a sort of secondary growth, and those also bounce back. And about 5% for jungle work, for the tropical work area that we're in, if we're lucky, actually are able to manage to hit the ground, and they also bounce back. So what happens is you get a sensor that is recording all of these returns, and it essentially develops what's known as a point cloud, right? It's a cloud of data that is, for any given moment, measuring many, many, many different distances that are essentially distances to the crown of that spot, to the understory, and then if we're lucky, to the ground surface. And archaeologists are interested in that final phase, and that the last 3 to 5%, which hit the ground, because what it allows us to do is see the ground as it's formed, and it's kind of a topographic form, underneath the trees, right? So here's a perfect image that was done by the company NCOM that has been contracted for a lot of this archaeological work. And here's the model that it creates of a point cloud, which is, here are all the returns that relate to the crown, the canopy top, right? This is what it looks like. Now, what you can then do once we get these data is categorize these points to be able to say, oh, this is vegetation of different levels, of different heights. So here are the trees at different elevations, 0 to 10, 10 to 20, 20 to 30, 30 to 40. And then through the magic of computers, you can deforest digitally. You can deforest this area and say, I'm going to take off all the trees, one class by another, and then by another. And below that, what do I have? I have the ground surface. But in this case, the ground surface includes a building that humans made that, for its shape and its geometry, cannot be understood as anything but human made, right? And so suddenly we have this set of 4 buildings that we would not have seen otherwise, right, from the surface. You can see the detail is so great that you can even see right here this little kind of indentation. This is an excavation that was an illegal excavation. We call it looting of this building that was left open, and it created sort of like a big trench in the building. And we can even see that degree of precision in terms of this particular building. We can see that someone came here at some point and tried to excavate inside into this building. So this is the degree of detail that we get. Sorry,
That's
John.
absolutely amazing, and it definitely kind of presages my next question. Was going to be about the first time I ever read about this. I thought, gosh, how does that canopy return being so large not obscure all the signal? But that makes perfect sense. Then let me ask you another question about a little bit in the past. You've written and spoken about in the past what an incredible experience it was, kind of finding thousands of structures in the middle of dense vegetation that were previously undiscovered. You've talked about what it was like sitting there with your collaborators as that first LiDAR data was uploaded. Can you tell us a little bit about that moment?
Sure, I'd be happy to. What I think is the best way to think about that is first to understand what it is that we have been doing up to this point. So you get the reason why it was so exciting, right? Because the emotional buildup our emotional reaction to this has a lot to do with our own personal experience of having worked in this area and tried to get images through our analog technologies or traditional technologies that have cost us frankly a lot of blood, sweat, and tears, right? So this is an example I wanted to put up of an image. This is an example of one of the largest Maya sites in Guatemala, called Tikal. This was discovered, quote unquote, or essentially Euro-American discovery of these sites in the 19th century by a British explorer traveler named Maudsley, Alfred P. Maudsley. And for him to be able to make some sense of just this particular site, you can see the amount of deforestation that he had to do simply to clear some of the largest buildings. These are all massive temples that we're looking at here. And they're peeping right above the canopy. They still are, and we'll go back to that in a moment. This is something that we've all seen, by the way, and I will get back to what reference that is in a moment. But this individual had to take all the workers he had and basically spend weeks cutting down just to be able to see the tallest of buildings, 30, 40 meter tall buildings. So you can imagine the rest of the environment where people lived, where people walked, houses and reservoirs and terraces, the kind of the grist of everyday life was entirely obscured and would be almost impossible to see, right? Unfortunately, modern day activities has led to a great deal of deforestation in the region. Cattle ranching, a lot of illegal activities, narco trafficking, and so forth, has created this unfortunate, environment that sadly allows us to see things like, so, I remember 20, 30 years ago, hearing about reading about Egyptologists finding a site by looking at Google Maps, right? And I was like, yeah, these guys in their pajamas wake up one morning, look at a Google map of Egypt, and voila, there's a site they can see. We'll never get to be able to do that, right? Well, now we sort of can. But with the deforestation, it, of course, was something that you can see this type of, drastic image of what we're looking at here. Of course, the cleared area makes for settlement survey, understanding where people live, how they live their houses, and so forth a lot easier because we're talking about very small things. The whole point is to try to do this digitally rather than in real life. And this notion of trying to get above the trees or getting to see through the trees was something that was appreciated 100 years ago by the earliest Maya archaeologists. Back in the 1920s and the Roaring 20s, even Charles Lindbergh, after his famous jump across the Atlantic, right, tried to put his hand into this and flew over the area that we were talking about to see if he could help his good friends who were archaeologists to figure out if you could see anything from the air. They really couldn't. I mean, they saw some things, obviously, and they were fascinated by what they could find and see, but it was still not the kind of penetration that they needed to be able to understand it. Even with modern day Landsat technology, and let's say 1980s, 1990s, with remote sensing coming into fruition, it gave better and better and better images of the vegetation. So here's a Landsat image that shows very neatly the different levels of deforestation between Guatemala and Mexico, right? This sort of artificial border, this yellow border that you see here, and you see how Mexico is much more deforested than Guatemala. Unfortunately, Guatemala is catching up. But my point simply being that these images were great for a whole host of reasons, and they got better and better and higher resolution. This is a QuickBird image, for instance. But all it was able to show was, well, here there are lots of trees because it's green. Well, now I can count the trees, right? 1, 2, 3. These are individual trees. Wonderful. But underneath all of these trees is what I'm really interested in, right? So even high resolution imagery was difficult in that sense. So what we were left with was this, right? From the 50s, this kind of plane table, alidade, theodolite, poor guys and the graduate students, usually in their 20s and 30s, sent off to go find sites beyond the main core. And these were two very famous archaeologists at Tikal, basically taking a break. It looks very similar today, maybe except the smoking, right? But essentially, this was the kind of work. And here's part of our project and what we have to deal with, right? So in the 100 years that people did research to try to figure out how people lived, where they lived, how many people there were, and so forth, the technology had changed obviously a little bit. Laser theodolites versus just compass and tape, but it was still the same. Got to go out there, and you got to cut the forest in little bits and pieces to be able to navigate it, right? And so this became part of the cost of research, right? And archaeologists were writing, even in their own publications, the green hell, beautiful as it might be, was still what was stopping us, right? So this is what all of us who of a certain age who did this we're dealing with. And even the satellite imagery that brought us some really spectacular discoveries and so forth were wonderful because they could tell us the things about where settlement might be, or very monumental things like this causeway that, this monumental causeway that goes across and you can see the vegetation differentially growing on it, gave us some inkling, but the rest was still a carpet, right? Here's an example. Here's where my site is on that image. You can see where the site is, where the site that I work at, that I do research, and there's no indication of anything below the canopy, right? Slightly better resolution data from NASA, from the space shuttle missions, and then essentially it only came down to our own map. And for about 10 years, maybe a little bit less, 7 years, I had students and myself working on a map on the ground. And we managed to do something like two maybe square kilometers. And it was at this moment, I remember precisely in the field, that I saw the Lidar results for one of the Maya sites. And I said, we're not doing this anymore. I don't know when I'll get Lidar, but that's what, we can't go on this way because it will dedicate too many resources to too many people. So what I'm trying to get at is that it was long, it was hard, it was arduous. You got the dangers of being bitten by a snake or getting lost, or just it required a lot of physical endurance. So much so that this is the large area that we study, right? You can see all the different countries: Belize, Mexico, and Guatemala. And the little dots here, all the little reds and greens and oranges, are all the areas that were fully surveyed after about 100 years of research. Like 600 square kilometers, essentially. There are a few that are missing in this one, but essentially 100 years, and we mapped 600 square kilometers all told, right? That's not a good average. I mean, that's 6 square kilometers a year. That's not that much, right? When we're talking about 60,000 square kilometers of an area. So then the LIDAR project comes in and within a month or two gives us data for 5 times that in 1 year. So when you think of it, that's the context within which that question that you're asking comes up. And it was, as I've said in other places, it's like, scales falling off our eyes, right? Boom. And all of a sudden, all the things that we dreamt or that we imagined or we mapped it, but didn't really know, and there was a lot of blank spaces, or it was a small little nucleus and then a lot of white around. Okay, I think that's how it goes. All of that disappeared, right? And we could just see. And when we opened up, we have a lab here at Tulane, and we have a big screen that we look at it. And there were a bunch of students. And I remember thinking, we put one image up, and there were about 5 of us. And then a few people walk by, and they get in. They go inside the lab, and then there's 7, and then they're 12, and then they're 15, and then they're 18. And we were all supposed to go to a talk at 4 p.m. That had nothing to do with archaeology. It was just an anthropology department talk. And none of us went because we were just mesmerized. We were just opening up one. And we weren't doing anything systematic. We were just looking. And, oh, my God, look, there's a temple. Oh, my God, look, there's this and that. So that was the sort of a fascinating moment of just being able to. And I had to stop at one point, and I said, everyone, stop. Before, I said, I want you all to remember this day, because this is the day in which everything changed for us, right? We went from not seeing and being really, seeing everything through a little pinhole to having our window opened up 100 times. And that really was kind of the most amazing thing for us. And to be able to make a map like this, right, where every little building that we find is isolated as a little yellow dot, turn it into a nocturnal image and say, this is what it might look like from 30,000 feet if you were flying over this region in 750 AD. Now obviously all the black here is because we don't have data from there, but you can see you can see places that are really dense, places that are less dense. Like what you do when you fly over the United States at night, right? Fly over Chicago, lots of lights. Fly over, much of the Midwest, and it's going to be a much darker landscape. And same thing for here.
Oh my goodness, that's a goosebumps moment. Thank you.
It is. That's exactly what it was. It was goosebumps. That's exactly right.
So that's actually, this brings me to something interesting. You've spoken before about how much those broad scale scans were able to tell you about the presence, density, and arrangement of structures, the sort of thing we can even see here. How do you get from those kind of facts on the grounds to the research that led to your insights around how the ancient Maya built and maintained socially politically complex societies over a millennia?
Sure. Yeah. And you know, well, you see something like this, right? And I need to stop and make a point that this research that began that gave us this massive scale of data in 2016 was really thanks to a consortium effort, right? Of projects that were coordinated by this foundation in Guatemala that said, this is what we need to do. Let's not think project by project, little bit by little bit. Let's think really at a large scale. So LIDAR is large scale in and of itself, but then the project itself was even larger than any LIDAR project. So it's like a factor to the factor in terms of scale. So instead of having maybe something 10 times bigger, it was 100 times, because this foundation named Pacunam put us all together and did this. So it's really a kind of a sea change in terms of not just the technology, but how we were put together, right? And what we were able to do is look at these images and these kinds of these landscapes of sites. And it doesn't take an archaeologist to recognize that this is a platform with 1, 2, 3, 4 mounds on it, right? And that these are natural hills in the background, but that these things here don't look so natural, and that these don't look so natural. And so that you have a landscape that's heavily mounded or heavily irregular, mountains to one side, a plain with all of these buildings and sites, right? This is not hard to see either, that you've got 1, 2, and 3 pyramids, even a moat, right? And then even look, this linear feature here that's like a wall and so on. So you could see all of these details just screaming out at you, that all you needed was sort of an ability to recognize linear patterns. It wasn't, of course, doing settlement archaeology and having that specialty helps, don't get me wrong, but it was very easy to appreciate for anyone to see. Even in this image here, you can see this line that goes across, that goes basically north here, or up in this image. This is a road that was built across the landscape, right? And if you notice, it doesn't swerve due to changes in topography. It goes straight. Doesn't matter, like a turnpike. It doesn't matter if it goes up or down, like the Jersey Turnpike. I'm going from point A to point B as fast and as straight as possible, right? And that's what this is. This is like not a little country road that goes with topography. So we could immediately see those kinds of details. Now, here's this image that I've shown before, and as I promised I would reference, this is the Rebel base in Star Wars. I don't know if anyone remembers. I know that Star Wars is now kind of a dated thing, much to my depression, I guess. But this is where, this is what I forgot, that even the moon, but whatever. This is where the rebels were, right? And it looked great in Lucas's movie because it was the canopy. Now LIDAR can tell us what the rebel base really looked like. And it strangely looked like a huge Maya site, right? And this is not a 3D enhancement with all sorts of, no, this is just taking those same data and extruding them into a 3-dimensional space. That's it, very simple. And so we can go from these large scale images of settlement across the whole landscape to very detailed images of sites, right? And where they are, the details of not just the big temples, but then, and this image here from one project, a French project in Guatemala, directed by Professor Philippe Nondedeo, but you can see all the detail, right? You can see the yellow line here, which is thought to be a causeway. Buildings are in red. White are things that are like modifications to the landscape. Blue are canals and wetlands. So while LIDAR gives us large things, it also gives us really small things. And so and now we have this map, right? And we can focus in, we can look at it at the large scale, or we can focus in on a small part of it and say, I want to study that building that I didn't know existed, but has these interesting features because, sorry, that was the next question, but because we can have this level of scalar precision, right? From the whole region all the way down to a single building, right? It's absolutely amazing.
Which does actually then kind of beg the question, are there situations in which almost like simple pattern matching becomes useful? Do you look for certain kinds of buildings? Do you let the algorithms do that work for you? Things that used to be doing but kind of manually.
Yeah, that's a great question. It's something that we're struggling with. I still am of the opinion that for the time being, the best computer for pattern recognition is the brain. You need to train it and so forth. But you're right. There are ways in which that can be sped up or things can be filtered, right? And so one of the things we do and I always talk about it again, this is my simplistic way of saying it, but it's like the glasses or the glasses that the Predator has in the movie Predator, where he can't see under certain, with certain wavelengths, and he changes it and suddenly he sees things, right? That's sort of what we do with these visualizations of the terrain models that we receive from the Lidar data. We're able to see the same features with different aspects emphasized, so that rectilinear features looks better, or smaller features or rounder features or whatnot, however we want to think about it, whether it's more topography based or more architecture based. And of course, in each one of these 4 images of the exact same thing, you can see everything in them, but you can see this little square of 1, 2, 3, 4 buildings is very bright here, and then you can see it in this particular image, this one a little bit less so, and so forth. But what you do is when you look at them this way, you can see all of the things that are slightly enhanced in one in the next, right? You can sort of see that mixture. So that's one way that we're doing it. So we go from a very basic 3D, what's known as a hillshade, right? It's sort of a 3D rendering, but in 2D, manipulated through various forms of visualization to then create an archaeological or a map that puts all of those features together using the protocols and using the standards that we tend to have in archaeology. This map would have taken a couple of years to do in traditional ways, and it was done in months because of it, but all done manually. We also can do things like volumetrics, right? We can ask the computer, we have these features that look like they're depressions. Well, how big are they? Right? Can we fill them? How much water? So then we can study things like hydrology. How much water is storable in this environment, right? These are things that are computations that can be done based upon this level. We can do presentations of settlement at different scales, what's known as dynamic binning, right? So you can sort of see it at this scale, or at this scale, or at this scale, depending on how we want to, what are we talking about? What are the phenomena that we're interested in describing? We can do topographic characterizations, right? This is really something that I've been a large part of this, was just trying to figure out topography, how the different classes of topography that the landscape, because essentially LiDAR gives us a topographic map, and then figure out where the buildings are in relation to these classes. Is there some pattern, right? So leveraging both the precision of LiDAR to find out little features, structures, buildings, and then using the topographic data to create models of topography. Things like costs, least cost paths, right? How did people move across the landscape, both locally and more regionally? These kinds of things can be done using these data. And finally, sort of machine learning algorithms based upon what we get from a manual analysis of a certain sample of LiDAR, right? Trying to figure out how that, and then combining that with other data from other sensors, optical sensors and satellite images, and then seeing if we can find a pattern that's local to that LiDAR that can be then translated to the rest of the region, so that maybe we don't need the precision of LiDAR for the whole area, but areas that could be defined as highly likely of buildings. This is something one of my students is working on. And this is sort of an image of I know it sort of looks like, just random black dots or black areas, but basically all the bright areas in this map are where the computer has said, based upon a whole series of, forest classification, right? Creating a series of relationships that then suggest, okay, based upon this and all of these layers of data that you're giving me, these are places where there's likely to be sites or buildings and so forth. And so that's where some of these questions are going in the future.
Well, and actually then You'll have to forgive me because I want to jump ahead and ask a
Sure.
question that's near and dear to me, which is,
Uh-huh.
so as you're using this aerial LiDAR platform for this, what are the main kind of areas of technical overhead? What are the things that, if they were improved, would really help you? Like, is it the posing and positioning of the plane? Is it something about the processing?
Yeah, I'll tell you one. The technical aspects of it, of course, as I've mentioned, as many archaeologists are jack of all trades, but masters of none, right? So we use and consume these data. Now, of course, if you tell me, oh, there's a lidar sensor that can emit 5 times more pulses than the one that you guys used, yay, great, wonderful. Of course, I'm going to say sure. And in fact, the one that NCOM used for the Pacunam LiDAR initiative was a really new one that hasn't actually been improved on, as far as I know, much since, right? So it's been the last 3 or 4 years. So that LiDAR survey that we did through Pacunam was actually using one of the most advanced sensors of the time. One of the things that I think is more to on what we can control, right? Because these technologies are developed in some technology heaven, and they just come draining down to us like, oh, look at this cool thing that some people invented, right? So I would love to have something that would, someone's going to say, oh, I'd love to have it penetrate the ground so that we don't have to even dig. That takes all the fun out of it. But still, something like that would be great. But those are sort of pie in the sky. But on our end, as archaeologists, one of the things that we need to think about more and are doing a lot of, but we still have to think about is how do we ground truth things, right? How do we go and check up on this? There's so much data that we've got. It took us 100 years to do 600 square kilometers. Now we've got 6,000 square kilometers of LiDAR. By that at that rate, it's going to take us way too long, right, to get to ground truth everything. So now we have to sort of recalibrate our own efforts to figure out ways in which we can go to the field and test or ground truth certain samples of the data that we have to make an informed opinion about the precision of the data and how much we can rely on what we see in the computer screen as being really what's out there, right? That's, I think, where a lot of interesting work has been done and will continue to be done, because I think that's where we're going to be able to then be comfortable with the data that we're looking at, even though we're not necessarily looking at it in the ground or looking at all of it in the ground.
That makes perfect sense. And actually, in light of that, the point about ground truthing can be done a couple of different ways. Have you thought about trying to cross-calibrate with other types of sensors? I'm not sure. Is there anything like, say, synthetic aperture radar or anything that
Right.
you're excited about coming on the field now?
Yeah, well, certainly. One of the things that we did. Let me see if I can go forward a bit. One of the things that my student and I just did. Here we go. We took the topographic patterning or the topographic classification that we were able to determine from the LiDAR of our particular research area. We call them polygons, right? These are the LiDAR captures. These squares here are all the squares, except for this one here, but all the ones that are sort of in reddish brown. Those are the ones that were done by the Pacunam LiDAR initiative that I'm part of. And this is particularly my region. And so what we did was we took the topographic characterization based upon our LiDAR data, and then we applied that same technique to readily available 30-meter SRTM or ALOS data, right? The elevation. These are surface models. They're not terrain models. They're slightly different, but for the purposes of a generalized patterning, they work fine, right? And suddenly we were able to expand our study. And this is actually something that was recently published, but what we were able to determine, looking at the data from our area here, was that Maya settlement, where people lived, is highly determined by certain topographic characteristics, right? Basically, in our area here, 90% of all the buildings we identified in the LiDAR are found on classes of topography that take up 20% of that landmass. So essentially, we're saying that 80% of the landmass is really not seen as habitable or preferentially habitable. Okay, so when you're now looking at a whole landscape and you're saying, well, 80% or 70%, it's going to vary a little bit, but a vast majority of it is not where they wanted to live. Well, that might explain why they're patterned that way. That might explain why their cities are like these mosaics, like I was talking earlier, of these garden cities, because it's not a choice. It's not all about a specific kind of way in which tropics are tropical culture societies are organized. Rather, no, this has to do with where you would want to live and where you wouldn't, right? Things of that nature. Things that might seem obvious to them, but that we're sort of still figuring out, right? I always use the example of New Orleans, where I am, right? The people marveled at the fact that after Katrina, some of the oldest places didn't flood. Well, of course they didn't, because that's where the French or Native Americans who were living there could see there was land that didn't get flooded, and that's where they lived. Over time, we've covered those areas and decided through human engineering that we're going to live in these places, but there's still lower lying areas that can be overwhelmed, right? So some things may become more obvious when you're just seeing the natural landscape in its original form. But what we are able to do is take those patterns, apply it to less resolved data, and still come up with really decent results of settlement settlement patterning based upon these lesser resolved data, which are free. Right. And so for certain things, maybe we won't be able to find sites like 1, 2, 3, 4, 5, count all the structures like we did with LIDAR in other data, but we can use the patterns we see with the LIDAR areas to then maybe inform the rest of the region. So that's one example that I'm talking about that really is a way of leveraging these different kinds of data based upon what you learn from LIDAR.
Oh, no, thank you. That's exactly what I had in mind. And I've actually been getting to have all the fun today, but we've got some audience questions as well. So what I'm going to do now is actually suggest that we switch over to that and take a few kind of live questions from the audience.
Sure. Be happy to.
So we've got this question from Jennifer Wang. What originally got you into archaeology and made you want to pursue it for your career?
I've always said that I've always thought that everyone at some point in their youth decides to be an archaeologist, right? Or wants to be an archaeologist. Well-adjusted and normal people grow out of it. And the few of us remain stuck on this idea and keep doing it. And so I just didn't get out of it. No, but in truth, I actually grew up in New York City. So I'm a product of Manhattan, right? I'm not an outdoorsy person that thinks of going to the outdoors all the time, right? So archaeology isn't something that you would encounter in that environment. But I had a lot of connections to family and so forth to Mexico, and so as a little boy, we would go to Mexico often, and not to tourism, just to be with friends and so forth, but of course we went to sites and so forth. So I learned very early on about the Mesoamerican civilizations, and I found them to be absolutely fascinating. And it's kind of stuck with me, right? And by the time I got to be about 12 or 13, I read a few books, and something clicked, and I said, this is what I would love to do. How does this work, right? And so my parents said, well, you can read, you take these books and so forth. And but both my parents are academics, and so my dad said, well, you should go to a meeting, you should go to a conference or something and see. And so he bought me this book that was all the rage in the mid 80s on the Maya that I read through and through. And at the time I was just learning, dates me, but I was just learning the language basic for computers, right? And of course, everyone thinks about the Maya in terms of calendars and the cycles of time and so forth. And so I decided I would write a Maya calendar conversion program in BASIC. Why not? And so you put in a date in our calendar, and it gives you the Maya date, or vice versa. And so to test it out, I tested out the dates from this book that I was reading. And just to make sure that I was getting it right. And 4 of the dates didn't work. And I remember I was telling this to my parents, and my dad said, well, you should write her a letter and let her know, and that maybe she can explain it to you. Pre-email, pre-whatever, right? This was just literally sitting down and writing on a piece of paper. And so I did. I wrote Dr. Sheely, Linda Sheely, who was at University of Texas at Austin at the time. And I said, dear Dr. Sheely, I'm this 15-year-old, blah, 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 blah. And she wrote me back and said, "Thank you so much." And she explained why two of the dates didn't work, and said, "Well, the other two actually found a mistake. I'm embarrassed. Thank you so much. Why don't you come down to these meetings that we have every year?" And so I went down as a 16-year-old or something. I mean, thanks to my parents for letting me do that, right? And fly down to Austin, sight unseen. And that sort of got me into the whole world, and I was able to go on a field trip. I mean, a field project that summer in Belize. And it kind of just took off from that. And it's something that once you do, I never know if someone's going to be an archaeologist until they actually go out in the field. And if they can enjoy that and really love it, because you can't avoid that part, then you know that this is for them. So hopefully that answers your question, but that's how it started.
Thank you.
You're welcome.
And the next question I think we've got, let's see. Okay. From Alan Morales, in what ways can the Maya of today be included to investigate the history of their ancestors?
That's such an important question. Thank you for asking it. So much of what's happened, and let me start by saying one aspect about this, which is that the Maya themselves do not see themselves exclusively as Maya, right? Maya is a sort of a blanket term for a group of people that live in this peninsula that I showed earlier. But the Maya themselves refer to them, especially if you go to Guatemala, they refer to themselves by more specific names like Cachiquel or Quiche, right? Maya is more like the word, maybe the term European, right? And then, yeah, okay, I'm a European, but I'm really Italian or Spanish or whatever. And there's a big difference between a Portuguese and a Pole, right? It's not like they would necessarily, just by being European, they're all the same. So it's really important to understand that diversity of today is very much a reflection of the diversity in the past. And we tend to have a sort of a normative view, the Maya per se, as if they were a single group, but they weren't. And that is part of what we try to understand is, how do they live? Are those differences visible in the way they lived, in the way they settled, or how they organized themselves in the landscape and so forth? So just to give that context, modern scholarship in Maya studies has been for the last 20, 30 years, heavily involved in education programs in Guatemala and Mexico and so forth, such whereby children in places like Yucatan and so forth learn the hieroglyphic writing system that they used. They learned the numbering system. I know that in Guatemala, part of the schooling of all Guatemalan kids is the Maya numerical system, right? Now, one might say that's a small effort and so forth, but there is this attempt to reintegrate or integrate the knowledge that their own ancestors had accumulated and hand it back to them. So there's educational parts of it, but more than anything else, there is just the inclusion of Maya in scholarship, right? That's happening more and more. There are more folks from Guatemala and Mexico who are of Maya descent, or not just of Maya descent, who are they self-ascribe as Maya, right? Who are studying archaeology, studying anthropology, linguistics, and so forth, and being epigrapher, learning how to the epigraphic system, and contributing. And of course, that degree of information, what I'm doing here, what we're talking about here, is a very kind of bird's eye view, right, from the literally flying over almost in some way, right? And obviously, there are other types of archaeologies that are more humanistic in their approach, more historically contingent in their interests, about specific areas, or focus on religion, ideas, ideology, thought processes, philosophies, and so forth. And those all have been inclusive, more and more inclusive over time. Obviously, we need to do more of that, but that's something that is a way that's been happening.
Thank you. And Professor, I think we have one more question. From Andrew Helton, you mentioned that only about 20% of land was considered to be preferentially habitable. What were the properties of this preferred land that were shared across settlements?
Great. Yes, good question. Well, I guess I guess, something that could apply to us in New Orleans is don't live in a swamp, stupid, would be kind of a simple way of reducing it. In fact, for many, 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 many years, for about 100 years, we understood that the Maya avoided the lower lying areas. If I go back to that map, let me put that map up. I'll just show it really briefly. There we go here. So this is, for instance, a map of the site at which I work, right? This is a more close-up, not of the whole region, but it gives a better idea. And what we were able to do in this particular study is create 4 topographic classes of land. And we found that the settlement, all the buildings that we could identify, were preferentially on what in this image are the yellow and light green splotches, these little islands. And what they are is essentially high areas relative to their immediate neighborhoods. Okay. Now, up until, for pretty much all of my research, we knew that the Maya would not live in swampy areas, the areas that are green, essentially the dark green, right? And so we said, oh, well, that's about half the land. So about half the land was habitable and the other half was not. Well, it turns out that a lot of the high areas, what we call uplands, right? The lowland and then the upland areas. The upland areas that are technically high are also small catchment areas or basins where water accumulates. Not bad places to farm, not bad places generally, but maybe not a place you'd want to stake your house on, right? And so the brown, which is this brown area, the brown areas are these areas that are still elevated nicely, but they are actually collecting water from all the nearby regions, the higher areas in the upland regions. So that was one kind of, we subtracted a lot of the uplands away because of that. And then in the lowlands, we were able to recognize that not all the lowlands are lowlands. There's distinction in there, and that there are some little promontories. And people had talked about this before us, but this is a phenomenon that's pretty widespread, we found, and that the settlements and those are those light green little islands. And those little islands are what we call islote type, which are little islands in a deeper swampy area. And those are also places where settlement or buildings are found. So essentially, very simply put, are the locally higher areas in what is in their neighborhoods, right? That's what separates. Not a brilliant discovery by any stretch, but the beauty is we can quantify it such whereby we can actually now compare this area to another region and say, well, this area doesn't have much settlement because guess what? It's got a lot less of the good land than it does over there because we can quantify it, right? So it gives us a way of comparing places that we had never been able to do before.
Thank you. Professor, this has been a rare treat for us today, and we really appreciate it. Thank you for coming and being willing to talk to us, and thank you for your research in general.
Oh, it was a pleasure. It was a pleasure. Thanks so much for having me.
Have a good day.
Take care.